Good afternoon, Ayush. Good afternoon, Srijeev. Good afternoon, Ruksha. Okay, guys, let's start off. We are at 2:15. So whatever the doubts I asked all of you to post in the Google Forms, I have started with what has come out of it. That the two, three things that have come out of it are AVL tree, B tree, B plus tree, and Tower of Hanoi. Other than that, there are some generic questions which I will answer. I will take up the doubt window and we will answer that in terms of the generic questions that are being asked. Beyond that also, if you have time and you have some doubts, we will definitely work on that. One quick thing that you need to remember, after this session, after the doubts are done, for around 10-15 minutes, what we will do is, we will not be live here. I will give you a separate Google Doc link, and there I would, whatever participants are left at that point in time, we will request those participants to come there, and I will make some couple of announcements there also, because I have been speaking for the last 24 hours now. I have not heard you, so I dislike this chat concept completely. Your emotions, your apprehensions, nothing is coming out. I just see some black and white text and I don't get to interact with you, which is very, very bad. I don't like this style of working. So I want to probably talk to you, understand you much better. So once we finish with the standard set of doubts, if there are other doubts or other topics to discuss, that's where we will come all together on a Google Meet, which I will publish at a later point in time. Come together, let's hear from you. I have some other things to also discuss there, which I will discuss in terms of your examinations, and what are the top priority things in the examinations that we need to focus on. Right now, with the examinations probably being talked about after 23rd of January, you have typically you will have 1.5 months now to prepare. So it's right time now to probably start thinking about what are the topics you will give more weightage on, and that's what I intend to discuss when we have this breakout session. For now, we will complete the standard set of doubts, then we will break out into a separate Google Meet where we'll talk about the suggestions, the etc., whatever we talked about just now, and on top of that, even if you have some more things, we can discuss that. So that's the plan of action for today. So with that, I will start. We have 46 of you here, which is good. I was not expecting so many because this is not the standard session. The entire thing that we plan to cover is already done. Only sorting is left. In case you didn't hear, when we will do sorting, next Sunday, 3 hours is what we have budgeted for sorting, and that time we will complete all the aspects of sorting. Yes, semester exam will be around the 3rd week of January. Okay, so now if we start off with what we wanted to do, that you had a concept on or a doubt on AVL tree. So I will not go through all the details that we discussed. I will directly jump into the concept, and I will directly take one example and try to follow it. Now, whoever had given this doubt, are you there in this call? AVL tree doubt was given by 2 people. Are you there in this call? If you are not there, I'll not spend time. Then we'll move on. I know who gave the this thing, but I don't know whether they are in the call. I'll tell you who gave it. Tell me if he or she is there in the call. Otherwise, we'll move on. Second person. So second person was Ragini. Ragini there in the call? Okay, yes, you are there. Fine. So let's go through this. Then Ragini, and it's for all of you who are part of this call. AVL tree is an important concept, good weightage subject or soaring topic. So let's be concentrated on that in case you still have doubts. AVL tree says that I am a binary search tree. That is the point number 1. That every tree that is an AVL will have to be a binary search tree. That is left subtree parent will be more than the less than the parent, and the left subtree of the parent will be greater. Right subtree of the parent will be greater than the parent. So that is what the binary search tree funda is. At the same time, it also says that the balance factor, which is the height of the left subtree minus the height of the right subtree, should be within -1, 0 and 1. That means the height should not be too different. That left tree is going like this and the right tree is chota, cannot be the case, right? So the heights have to be near. That's what it is trying to say. So in case we have a tree like this, let's say if we have x is less than y is less than z, and this x, y, z, let's say, are numbers, right? In that case, when we actually plot these numbers, then they will look like this: z, y, x, right? So this is what it will look like, and this creates a problem because the balance factor which we talked about just now, which is height of the left minus height of the right, everything is to the left. So the right is 0. So which means the z, which if we calculate the balance factor for z, then it will be the height of z minus height of z on the left minus the height of z on the right. Height of z on the left is how much? 1, 2, right? So then 2 is the height of z on the left, and on the right the height is 0. So we get 2, and 2 is not part of this. So it is creating a problem. So if this creates a problem, then we will move on and say that we will have to fix it. Now the fixing of AVL tree is always through rotations. So to rotate this, what we will do is, we will, when my acronym, or to remember, the way I remember it is, why did we land up in this issue? We landed up in this issue because we went left, left. Both the times we went left. From z to y also left, y to x also left. Because both the times we went left, so we will actually be fixing this problem by doing an ulta. Ulta means if both the letters are the same, that means they signify left. Then to fix it, I'll do a ulta, which means I'll do a right rotation. Right? So that is why it is written right. So I will fix it by doing a right rotation. Right rotation from where? From the top. So if I do a right rotation, what will happen? I will be pulling z down and I will be pushing y up. Right? So I will be pulling z down and pushing y up. So if that is the case, that I'm pulling z down and pushing y up, then my tree will look like this. My tree will look like y, x, z. So this is what will happen. Z will come down, and x will be at the bottom, y will go up. So now y is, what is the balance factor of each of these? X is 0 minus 0, left subtree is not there, right subtree is not there. This is 0 minus 0, and this is what? Left subtree is 1, right subtree is also 1. So everybody is at 0 balance factor, which is allowed because 0 is already here. See, 0 is here, so it is allowed. It should not be greater than 1, plus minus 1, right? So that's what it is saying. So this is how you will balance. So this is now a balanced subtree or a balanced AVL tree. So then if this one use case is understandable, then the next use case is next use case will be like this, that I will take let's say if this is how my my unbalanced thing looks like, then Z, Y, X is what my unbalanced looks like or imbalanced looks like. Then everything is to the right. Z therefore has 0 to the left and 2 to the right. That is the height of the right subtree is true. So minus 2 is coming. Minus 2 is not allowed. It's not here, right? So it's not here. So there is an imbalance. So to fix this imbalance, you have a right imbalance. So do an ulta. So what the ulta is, you will have to do the ulta of the letter. Right means the ulta is left. So you will do a left rotation. So that is why you will left rotate. Where will you do the left rotation? You will do the left rotation here, right? So that is what you will do. And if you do that, then Z will come down, Z will come down, and Y will move up. So if you do that, then this is how it will look like: Y, Z, X. That is what you see here. So this is the second use case. The third use case is when you have a jagged AVL tree. When a jagged AVL tree means that it is not left, Z, Y, X. Suppose this was the case. Then why did this problem? Who is creating a problem? Z is creating a problem. Why? Because Z has left tree as left tree height as 2, right tree height as 0. So it has a problem. So that's why if this now creates a problem, why did this problem arise? It arose because left and right. So if it arose because of left, right, then these two letters are different, right? So don't do ulta. Ulta is when the letters are the same. If the letters are different, then you do what the letters say. What do the letters say? Left and right. So do a left rotation. Do a left rotation. And the left rotation, because we are doing 2 rotations, we will halve it up, right? So we'll do it at the half. We'll do it at the half point and we will do it at a left rotation. So this left rotation, when we do it, then what will happen? It will happen that Z will come down, X will go up. So if that is happening, then what is happening? Z, X, Y. This is what will happen. Sorry, my bad. Yeah, so if X goes up and Y comes down, then what will happen is, if X goes up and Y comes down, then we will have, yeah, I was right actually. X goes up and Y comes down. So we will have Z, Y, X. And when we do the rotation, this X will be going up. So X goes up and Y comes down. Right? So that means that you now get what? You now get a tree which looks like this tree. Right? So that's why you have to do a right rotation. You have to do 2 rotations, right? LR means you have to do 2 rotations. You have to do left rotation and right rotation. So the right rotation, because now it is an RR case, the discrepancy is because of left. So it falls under this case. So evidently you have to do anyways a right rotation. This is also telling you to do the same right rotation, the same thing, right? So do the right rotation. So that if you do the right rotation, then Z will come down, and X will move up. So then what will happen is you will have X here, Y here, Z here, right? So that's how this problem will be fixed. Now with this, if you do one more case, which is the right left says that if we have a problem like this, Z, Y, X, then we have a problem created because of right left. Z is imbalanced. Now Z is imbalanced means we have a problem created because of Z. So to fix this, we have to do right left rotation because the letters are the different. I told you to remember it like this, that if the letters are different, then do the what the letters say. So we have to do a right rotation, and because we are doing 2 rotations, right and left, we'll have to do it at the half point. So let's do it at a half point, right rotation. So if you do it at a half point, what are we saying? We are saying that X will go up and Y will come down, right? So X will go up and Y will come down at the half point, right? So then the resultant tree will be Z, Y, X, right? So this is the resultant tree. And when this resultant tree comes, then you are actually creating one more problem, which is your right problem now. So right problem means that you had to do a left rotation. So you have to do a left rotation like this, which anyway this is also telling you to do. Do the second one as left rotation. So you did the right and then you have to do the left rotation. So this is why you will have to do the left rotation. Left rotation means Z will come down, Y will go up. So Y will go up means Y goes up, Z comes down, X goes right. So that is how these 4 cases will come at various stages when you try to solve things, right? So let's see one solution now. Let us do this solution. So give me 30 seconds. We will start this solution now. And when we do this solution, what you will see is that the exact nature of the rotations is what we will talk about. So let's start off with 12. So why that we are what is an AVL tree? A binary search tree. So when we start off, we will be starting off by highlighting the case that we are working on. When we work on this, all the nodes that we will put will be as per the binary search tree, right? So AVL tree has to be binary search tree. Then comes the fact of height. So 12, then 11 will go here because of the binary tree concept, right? So now tell me one thing, is there any imbalance? There is no imbalance. 11's balance factor is 0, that is 0 minus 0, right? And 12's balance factor is 1 minus 0. So there is no imbalance, right? So all of it is perfectly allowed. Now we have to add 13. So 13 if we add, then 13 gets added here. Now is there any imbalance because of 13 getting created? No, because now 12's balance factor is 0 minus 0. Left is 1, right is 1. Leaf nodes will always have 0 minus 0. So they are also balanced. So there is no imbalance. So this is how the imbalance is calculated. I will skip imbalance for now. I will tell you when there is an imbalance and then you can calculate there. Now we are supposed to add 10. Now 10 gets added to the left of 11 because it is a binary search tree. Does it create any imbalance? It doesn't create any imbalance. You can check it out. It doesn't create any imbalance. Then we will add 9 to the left of 10. Does it create any imbalance? Let's see 9 if it creates an imbalance. Balance factor for 11 has gone for a toss. Calculate the balance factor for 11. Balance factor for 11 is looking like this. Left subtree is 2, right subtree is 0. So we get 2. So balance factor is gone. Therefore, this particular tree or subtree is a problem. In this particular subtree, what use case do you see? You had seen 4 use cases here. What use case do you see? What is the problem? Just figure out what is the problem. The problem is because of what? Left. Now left creates what? Left is the same letter. I told you when the same letter comes, you have to do the ulta. Ulta is right. So do a ulta rotation right. So if you do a ulta rotation right, what will happen is 11 will come down, 10 will move up, right? So 11 will come down, 10 will move up, means your balanced tree will now look like 12, 10 has come up, 11 will come down, and 9 will be here. When you are doing this, just remember that your BST should not be violated. So you move 10 up, 11 has to come to the right of 10. It will come down, but where? Left or right? It will come to the right of 10 because it is a BST, and 9 goes to the left of that, right? So that is what is happening here. With 13, we complete this second step. Now what we are getting is 15. So when we get 15, then we will insert 15 to the right of 13 because it is a binary search tree. Now does it create any imbalance? It doesn't create any imbalance. Now we are taking 14. Now 14 we will be inserting to the left of 15 because when we search for 12, 14 says I am greater than 12. I went here. 13 says 14 is greater, so I went to the right side. Right side I get 15, which is becoming more than 14. So 14 I have to place here. So 14 is placed there. When we place 14 there, what happens is the balance factor for 13 goes for a toss. So if you see the balance factor for 13, what it is, it is having only the right root. So the right child, so 2 is the right and 0 is the left. So 0 minus 2 is minus 2. So that's why 13 is gone for a toss. Why did 13 go for a toss? Because there was a right left problem. So this particular subtree has a problem, right? So that problem we'll have to fix. It's a right left problem. So when there is a right left problem, what did I tell you? Letters are different. So you have to do 2 rotations. In what order? Right and left, in the same order as the letters. Where? From the half point, because you have to do 2 rotations. Do it from the halfway mark. So if you do it from the halfway mark, 12, 10, 9, 11, and then you have 13 will be there as it is, and then we are doing a right rotation. So if we are doing a right rotation, then 14 will move up. Now 14 is greater than 13, so it will go to the right, and then 15 is also greater than 14. So that is how I will build. So when I am doing this, please remember you are doing a BST concept when you are doing the rotation. After rotation, please follow BST. This creates a problem. What problem? You have a right problem. Because you have a right problem, right left was advising you that my second rotation should be a left. Yes, your second rotation should be your left, because we have an imbalance here. So we are doing a second rotation left. So that second rotation that we will do is going to be 12, 10, 9, 11, and we are doing a rotation, means 14 will come up. On the left will be 13, on the right will be 15. So that takes care of my, what is the last thing that we did? 15. Now we will take the next thing which will come in, which is going to be 18, I guess. Yeah, so we took 14 and that created that imbalance. So now we will take 18. So 18 will go where? 18 will go to the right of 13. So 18 will go to the right of 15 rather. 18 will go to the right of 15. So 18 goes here. I think there is a problem. 1 minute. Let me figure out the problem. Yeah, I think it's not right of 18 is greater than 12, 18 is greater than 14. So it will go to the right. Yeah, I think which is right. 18 is greater than 14. Then 18 is greater than 14 means it will go to the right. 15, 18. I think it is right. Small brain freeze moments, guys. Sorry for that. So, yeah, so 14 greater than 15. Okay, now this is okay. Now then what we will do is, does this create a problem? The 18 positioning doesn't create any problem. Everybody is balanced. Now, what do we do is, we will now need to see what is the next element, 7. So let's take 7 and insert. So 7 will go where? 7 will go to the left of 9. Right, so 7 goes to the left of 9. Does it create any imbalance? Doesn't create any imbalance. So then we will take 6. 6 will go to the left of this. Does it create any imbalance? It does not create. There is an imbalance. There is an imbalance at 9. Right, so there is an imbalance here at 9. So when I see this imbalance, why did this imbalance happen? Why did this imbalance happen? This imbalance happened because we went left. So if you go left, what do we have to do? We will have to do a right rotation like this. So when we do that right rotation, how will the tree look like? It will look like 12, 10, 11, 12, 10. Then we are doing this rotation. Rotation will move 7 to the top. So 7 comes to the top. 6 goes to the left, 9 goes to the right, and 10 has 11 here, and 12 has 14 here, 13, and then we had 15 and 18. Okay, now next is your next element that is there is the last element, I think, okay, last but one, 5. Where will 5 go? 5 will go underneath of 6. Does it create an imbalance? Yes, it does. If 5 goes underneath of 6, then we have an imbalance at 10. So 10, if you see in 10, what is the left subtree? Left subtree height is the highest height, right? So we will have the highest height of the 10 will be 1, 2, 3, and the right subtree is the 1. So 3 minus 1 is 2. So there is a imbalance of 2. So that imbalance we'll have to fix. So why did this imbalance come? The imbalance came because of this, right? So because of this. So what is the problem here? Left and right. So left and right. So imbalance, how will you identify the smaller subtree? You start from which node has the problem and take 2 nodes below it. So that is your left-right problem. So this imbalance is because of left and right, and because you have a left-right problem, so the left-right problem has to be fixed by using a left rotation plus a right rotation. Same letter I told you, take the same thing. So if you do a left rotation, then you have to do a left rotation here, right? So if you do a left rotation there, then what will you get? You will get the following tree. So the tree will become 12, 12, then 10, then I'm sorry, 12, then it is okay, 12, 10, and then we are doing a left rotation. So 9 will go up, and then 7 will come below, then there will be 6, then there will be 5. So this is what will happen. And on the right, whatever is there will be there. I'm not drawing it because we still have to do one more rotation, which is the right rotation, right? Because we did the left, but then we created one more problem now, that this becomes unbalanced, right? So what kind of imbalance is this? This is a left-left imbalance. So we have to do a right rotation, and that is what this was also suggesting you to do, a second right rotation. So this is that right rotation we have to do. Now let us draw the complete tree. So the complete tree will look like this: 12. Then we are doing a right rotation, means 9 comes up. Then we will have 7 on this side, 10 on this side, right? And then we will have 6 on the left and 5 on the left, right? So that is what we will have. And let me see, 12, 7, I did miss something. Yes, I did miss something. In fact, I should have drawn this right side. I did not draw, which is why I missed it. So let me just go back and correct it. So we are till here, it was okay. Now we are going to do a right rotation. Before right rotation, there was an 11 here. We should not forget that. There was an 11 here. And then you had your 14, 13. I'm just drawing it so that I don't miss out anything. 15, 18. Right? So we are doing a right rotation now. And this right rotation will mean what? We will have 12. We will have the right rotation will happen at 10. So 9 will move up. 9 will move up. And once 9 moves up, we will have to the left of 9, we will have 7. Then we will have 6. Then we will have 5. And to the right, we will have 10. And we will have 11. And then we will have 14, 12, 15, 18. This is what we will have in this situation. And therefore, now you will see that everything should be balanced. So do we have a problem now? We don't have a problem. Therefore, next is the final key. 4 will go to the left of this. So 4 will go to the left of this, which is left of 5. And this left of 5, when 4 goes, there should not be any imbalance at the left of 5. There is an imbalance here that has been created. This imbalance should be fixed, which means that we will need to fix that imbalance by saying that this is a simple imbalance, so we will fix it directly. So we'll say 12, 9, 7, and then comes the imbalance. So 5 will move up, 4 will go to the left, 6 will go to the right, and then we will have the imbalance fixed. Then we will have 10 here, 11 here, and then we will have 14 here, 12 here, 13 here, or 15 here, and 18 here. So that fixes the imbalance. Now everything should be in a proper balanced manner. So that is something that will be the solution. Now I don't know whoever asked this, whether this became problem. The problem is okay. Whoever Ragini, yes, I remember. Ragini, is it okay now? Just confirm so that we can move to the next topic. Okay, I am unable to hear back from Ragini. I am assuming that it is okay. Let us move on to the next topic. So Ragini, let me know if it's still not clear, then we will do a separate session. So that's on this particular problem. Okay, so Ragini has responded yes. Just because I'm asking, don't say yes. If it is not yes, please tell me no. I don't mind explaining one more time. Is there any restriction to rotate different degrees of nodes? I didn't understand the question, Partho. If there is a BF, which means a balance factor issue, you will rotate. Different degree of nodes means you are saying that whether it is at a different height. You have to give me a situation, Partho, and then I can probably say whether there is a situation problem. Okay. Prims and crucials typically doesn't come, right? Prims and crucials I have rarely seen coming. So I'm not going to discuss prims and crucial unless you really want to, because it's actually, if you ask me, if it's part of your DAA course, which is coming up. It's not part of this course, but still some fantastic examiners are there, right? So they will create questions like that. ZXY in AVL first slide. Whatever it is, there could be a typo, but I think Srijiv, if you understand, that is okay. Now let's move on to the next topic, which is our B tree. So from a B tree concept perspective, let me go to the topic. Yeah. Okay. Okay guys, so B tree, whoever did not listen carefully yesterday, please pay attention. B tree, we will go to that area. In B tree, we have 34, 67, etc., etc. We have to consider this as a B tree, or construct a B tree. So first let us see what is a B tree. We'll go to that example. But what is a B tree? We said that first thing that you need to understand is, we were all the while creating trees like this, where this was your data. The data was being kept inside the tree. And when you are keeping data inside the tree, if you want one data, it is okay. But if you want both A, B, C, then what will you have to do? You'll have to go to A, you'll have to go to B, then you'll have to go to C to get the data. Right? So instead of that, B tree says that I will give you a way by which you can have both the worlds. You will have both the tree as well as you will have the you'll have both the tree as well as you will have the way to get more data from one node. So more data from one node means that you'll have to convert that data or a set of data into one key, which means one key will look very big now. Let's say one key will look like this now. So instead of having one single data inside the key or inside the node, I will now have multiple data inside the node. Multiple data inside the node. So I will have data like whatever data I can have, I will have. And if you remember, each of these trees are having Yeah, so each of these trees are having how are they created? Yesterday we had discussed that each of the tree nodes are created using double linked list. So you have a previous pointer and you have the next pointer, and here is your data. So that's how every tree element will be created, every tree's node will be created. So if that is the case, then this will also be looking like this, because that's anyway a key, right? It has to be created through some data structure, so double linked list. So in that case, this will have a left pointer and this will have a right pointer like this, right? And the data will be here. So let us say the data is K1, which we call as key 1, right? So this will look like this. And my second element here will also be a double linked list. So this will be K2. So it will also have its own left pointer and its own right pointer. And my third element will be K3, having its own left pointer, having its own right pointer. And my fourth element is K4, having its own left pointer and right pointer. Now these two pointers have no significance to stay separate. The reason behind it is being, it will point, one pointer pointing here and one pointer pointing somewhere else does not have any sense, because both of them should be greater than K, because it is to the right of K. Both of them are to the right of K and both of them are to the left of K. So both of them exhibit or should be actually doing the same thing in terms of making this node, whichever this child node is, if it is to the right of K, then this child C1, who also has a left pointer and a right pointer, this child should be greater than K1 and this child should be less than the K2, right? So that is where I am saying that from, if you consider it from a K1 perspective, then both of them are saying that we should point to somebody who is greater than us, because we are doing the right linking. K2 says we should point to somebody who should be less than us, and both of them should be satisfied, but both of them should therefore be one single entity. There cannot be two pointers doing the same thing. So which is why there will be only one single pointer which will help you in between the nodes to point to the right element. So then where will we point? We will point here. And this, let's say, is C1, this, let's say, is C2, this, let's say, is C3. These are my child, right? So what I'm saying is that I am not taking away the fact that I'm still giving you a tree. I will still give you a tree, and the tree will have multiple value in its node. T will have multiple value in each of its nodes. So this is that multiple value. This is one node, it has multiple values. This is one node, it could have had multiple values, I just kept one value, right? Just for the simplicity's sake. So then this will attach itself to this part. Then we will have one more thing where this will attach, and we will have one more child which will attach here. So mind it, all these are actual keys, but they are also child, because I said I'm not going to take away the tree benefit from you. So you will have parent, child, parent, child, parent, child. It's only that the parents are now not one single parent. They are multiple parents, multiple childs put together in one node, right? So that's what you have. What does this mean? This means that C1 has to be less than K1. And of course, because it is on the left pointer of K1, so C1 has to be less than K1, and C2 has to be greater than K1. So C2 has to be greater than K1. And at the same time, C2 has to be less than K2 because it is at the left of K2. C3 has to be greater than K3. And C3 has to be greater than K2. And C3 has to be less than K3. C4 has to be greater than K3. And C4 has to be less than K4. And C5 has to be greater than K5. Right, so that, sorry, K4. And that is what the conditions of these childs will be for you to take a call of whether you are doing a proper binary search tree or not. Right, so at the end of the day, this should also be a binary search tree. So B tree, internal things will be a binary search tree, and instead of keeping one node, like in a binary search tree, you will keep multiple values in one single node. That is, we call them as multiple keys in one single node. So that is what is a B tree. Now with that, this part is over, but then how many such elements can you have here? How many keys can you have inside a node? That is defined by the order m. When it is given as 5, this would imply that the number of keys that you can have is m minus 1. This is the number of keys that you can have at max in a particular layer. So which is equal to 4. So for m equal to 5, we have 4 keys, as you can see here. These are the 4 keys that we have for m equal to 5. Because they said m equal to 5, I created, let's say, something like this. 4 keys. Right, so that is what this is. And this m equal to 5 is nothing but your children. There are 5 children that I can have because m is equal to 5. So I hope that is how you understand a binary tree, or what a binary tree is. Questions come on properties of binary trees, so please be careful about that. Questions say that maximum children is m, maximum keys is m minus 1. This we already know, right? We have just now discussed. But the minimum children is ceiling of m by 2 for a non-root node. That means if we have any non-root node like this, if we have a something like this, then the minimum children that I can have for a non-root node means I am here. Right? So if I am here, what is my minimum children I can have? I need to have ceiling of m by 2. In this case, what is my m? This is 1 key, 2 key, 3 key, 4 key, 5 key. That means my m should be 6. Right? Because my keys are 1 less than m. So m by 2 is going to be 3. M by 2 is going to be 3. So 3 should be the number of children that I should minimum have in order to justify this particular tree. And how many elements I have here? I also have 3 elements here, but that has nothing to do with the 3. The other 3 is I am counting this. How many children are there? So these would be the children to this particular tree. So similarly, there are other relationships that you will have to remember, and also remember the fact that this and this, when you place the elements here or here, these will be sorted from left to right. Right, so that is something you have to remember. The key child rule, I have already told you how you will place this child, in which direction you will place this child. This will be basis the rules that we have identified. So the same set of rules I have already written in the last example. Now let us move into a practical way of understanding how a tree is, and then I think this thing will be much more clearer. So let me see the window first, chat window. Is there any extraction? Okay, no sir, understood sir. Will you discuss Prim's a little VZXY? Wheel side R keys treat. Arunima, I didn't understand. R keys treat. Oh, you wanted to say R keys treated as something, right? So it went off. Just type the complete message, then I'll come back. R keys treated as root element. No. Everything is a key, not just the root element. Everything is a key means that if I draw a key like this, a node like this is a node. Then the keys are inside these nodes. The key is your data, K1, K2. This is your data, right? And this data is inside your node, and then comes your children, right? So the children is, let's say, like this. This is your KC1. This is your KC2. This is KC3, and then you have one more children, which is child node, which is KC, or this is K1C1, K1C2, K1C3, and this will be, let's say, K3 or K2, K2C1, K2 C2, K3 C3. I'm just trying to name them something, right? It's not a multiplication of K1 and C1. So if you see here, this is also a key, this is also a key, this is also a key, but this is not a root element. This is a key, this is a key, this is a key, this is a key. So this is a root element. This is a key, this is a key, this is a key, but this is not a root element. So the keys need not be in a root element. Keys are data. They can be anywhere. Root child does not matter, Arunima. Is that okay? Just let me know if it is okay, Arunima, unless you have understood it. Okay, now let us move on. We have 34. So we are now going to create a B tree from this entire set. How will we do it? Let's do it one step at a time. So we will do 34 as the first key. First of all, how many keys can I keep in one node? M equal to 4, K equal to M minus 1, that is 3. So the total number of keys that I can keep in one node cannot exceed beyond 3. So 34 I put here, 67 I put here. Remember, while putting it here, you have to maintain the order, ascending order. So this is already in ascending order, so I put 89 also here. Now 990 wants to come, but 90 is a poor guy, it cannot get inside because there is no space. So then the fun starts. Then we create a promotion rule. Somebody has to go up so that 90 can be accommodated. Somebody has to go up so that 90 can be accommodated. So what we will do? We will do a median calculation. 34, 67, 89, 90 is 4 elements. 4 elements divided by 2 is 2. So at position number 2, you can actually create one median. So the median at position number 2 can be to the left of this line or can be to the right of this line. So it can be either this or it can be either that. So any one of them will move up. Any one of them will move up. Either 67 or 89 will move up. Right? So 67 or 89 will move up. I will take left side of that line to move up. Right? So 67. My median will always be one less. That is, I am taking floor in that sense if you want. So what I will do is I will therefore take that particular element. Now if you would have had 5 elements, it would have been easier. See, if you had 5 elements, then you know what is your half point. Your half point will be here. So this you will take directly up. Right? So that you have to take this one up. But here you can't know half, right? So that's why you take any one. And I'm taking the left one. So then 67 I have to move up. So 67 I will move up. 67 has no place here. So that creates a place now for 90 to come in. Right? So that creates a place for 90 to come in. And that's what I'm saying, that now so for 90 to come in, that creates a place, but I am not going to say that 90 will come in here or 89 will be pushed. I'll not say 89 will come in here, 90 will come in here, because I will have to split it at the right side of this will be in a different section altogether. So there will be a new key that will get created because of this overflow. And that new key therefore will mean that 89 will come here, occupy this place that is on the new side. So this is how it will look now. So again, you will have 3 keys and you will have your 89 and 90 because this was on the right side. So this is also on the right side that you are creating, and here you will place your promoted element. Promoted element will be here. That is also a 3 key node. The promoted element is 67. Now you figure out what are the pointers. How will you connect 34 with 67? the left side, this is your previous pointer of 67. So this previous pointer of 67, this one, if you can't see it, this one is what I am talking about. This is the previous pointer, this is the next pointer. This is the previous pointer, this is the next pointer. So I hope you can understand. So that left side, which is a previous pointer, binary search tree says that I should be greater, so it goes 34 should be going this side. 34 should be less than 67. And 89 and 90 is greater than 67, so it should start from this right pointer. So we will take it right. This is how your tree would look like after 90 is inserted. Now 100 comes in. So 100 comes in, very nice. 100 can come in here, right? So that is easy. It had a placeholder, it went inside there. Now 2 comes in and 36 comes in. So when 2 comes in, then 2 should be coming here, but 34 is here, so we will move 34 to the right. So we will take 2 here, move 34 to the right, and then 36 will come in, so we will take 36 here, right? So then this is how your current situation will look like: 2, 34, 36. Now 76 will start. 76, where will it stay? See 76. See 76, when I compare with 67, it is greater, so it will be in this side. And when I said this should be sorted, so 76 should be somewhere here, right? So 76 is here, and that is creating an overflow. Write it to the right. 76, 89, 90, 100. Split it here, take this to the top. Same logic, take this to the top, take 89 to the top. Right, so split it and take 89 to the top, and that would mean that now you will have something like this. So C2, even if you wipe everything off, don't worry, because everything is written on the right. So see what is written on the right. So 89 has gone up. So who remains? Only 76 remains, and 76 will have 3 keys provisioning, and who is created new? 90 and 100. Told you, right? When we split, the right part will be creating a new node. Now see the pointers. Check all the pointers. Don't just check the pointers related to this, because you have put 89 above, so that might create a different story. So 67, there is not going to be any change, but 89 there might be a change, because 89 came up. So 89 is left. That means this set, this entire set should be less than 89 and greater than 67. This entire set again should be greater than 67. At the same time, it should be less than 89, and that is how it is. So it is okay. And this set should be greater than 89. Right, so this set would be greater than 89. There is no element here for me to check. There is no element here for me to check the other side of the story. So I am not going to check it now, at least for now. So this is 90, 100. Now, next 53. So 53 will go. What is the next element coming in? 76 to 34, 36. Yeah. So now 53 will come in. So where do you think 53 can go? 53, when it comes in, it is coming in from the left, because it is less than 67. So it will come in here, and it has to come here, because I said this will be sorted. So this is where it will reside, creating an overflow, right? So this is where it will reside, creating an overflow. So write the overflow here: 2, 34, 36, 53. 2, 34, 36, 53. So if that is the case, then we will move 34 to the top. When we move 34 to the top, then all of this will move to the right, because it has to be sorted. Right? So 67, 89 and 34, which means 34, 67, 89. So 34 has moved to the top. So what I will do is, I will omit yes, I will omit all of this and I will create 2 fresh keys, one like this and one like this. Why did I create 2 fresh keys? Because this 2 has to stay here and this 36 and 53 has to go here, right, the same way. So then 34 will be pointing where this 34 should point to this 2 properly, which is okay. Check the pointers is the next step. So that check pointers is what I am doing. 34 will point, 2 is less than 34, okay. But 36 and 53 is greater than 34. So this pointer should point here and not there. 34 and 36 and 53 is greater than 34. And it is also less than 67. Mind it, check the other side also. 34 and 67, 36 and 53 is less than 67, greater than 34. That's why this pointer is valid. And on the other hand, this 67, we will omit this and we will now see that 76 is greater than 67, less than 89. That's why this pointer will now point here to the 76. 76 is greater than 67, less than 89. And then 89, this pointer is what I'm using, and 89 will have 90 and 100 greater on the right side of it. So this is how your intermediate node now will look like. So we did till 53. Now we will go to 51. Now 51 will go where? 51 will come here inside this 53. So 53 will move right and 51 will come here. So 51, 53. Then we have 12 coming in. So 12 will go here. Then we have 10 coming in. So 10 can go here if 12 moves to the right. So 12 will move to the right and 10 will come here. And then 77 will come here, which will go to after 76. And then we finally, I think we have 69. So the 69 will go before 76. There is a space, so 69 will go before 76. So we will have 69, 76, 77. So this is your final B tree that you have. Now if you see, you will have 3 data in each node. All your leaves are at the same level. These are the characteristics that it is satisfying. Your pointers are perfect and you have not used more than 3 keys because you were not allowed, and you cannot have more than 4 children because M is 4, and you don't have more than 4 children. You have 1 children here, 1 children here, 1 children here, 1 children here. That is what you have. So this is B tree. So B tree clear, everybody? Okay, not okay? Can you write it? Okay, good. So B tree is clear. Now we'll go to B plus tree. Fine. Now B plus tree, let me go there. Now in B plus tree, it is completely similar to B tree. The same funda that I will give you multiple keys inside a node rather than 1 key. Right? I'll give you multiple keys inside a node. The funda remains the same. Only thing I'm saying is that these multiple keys that are there inside this node, when it goes and attaches itself to somebody at the top, this top person will not have the data, which means K1 will not be at the top. We were promoting, right? Things from the bottom which were overflowing, we were putting it to the top. That means the actual data was moving to the top. Here we will not move the actual data. So these people who will be here, let's call them as R, R1, R2, R3, R4, R5, or whatever that is, right? They are called as routers. Their job is to guide the person who comes here to say where or which path they should follow to reach a particular value. So if I want to search for K3 and I come here, then it will say go this side. You'll get K3. So I'll get K3. As soon as I get K3, there is also one good trick that they have done. They have done a forward pointer like this. That means K4 is connected to K5. And likewise, if I have one more block here, one more block here, all the blocks are interconnected through linked list. So if I have actually came to R in this block and then I asked for K3, it said go here. I came here. From here, I can get all the nodes. That is the beauty of this B plus tree. So if I need large amount of data in one shot quickly, I will come here. I will ask it where. It will say here. Okay, I'll go here, run a loop in iteration, and I'll get all of that. One shot. I don't need to do any recursion, any kind of tree traversal. Everything is here in one shot. So all we are saying is data is here and this is router. If there were some more levels above, like this, these were also, all of this will be routers, all of this, except for the leaf, everything else is a router. Everything is in the leaf, everything is in the leaf. That is why we are saying we will not move the data above, because then everything will not be in the leaf. Then if I come to K3, will I get all the data? I will not. Somebody would have moved up because of the overflow. I will not get all the data. So that is why we will say that we will keep everything in the leaf. Now how do we do that? Let us see that. So let us take this example. In this example, we will we have said we are saying 4. So if this is 4, then our M is 4, our K is 3. So again we have to build a 3-pocket node like this, a 3-pocket node like this, and this 3-pocket node is a data, because this is a data, so I will keep this in the data. So definitely then this will be my leaf level, this will be my leaf level, right? So it cannot be any other level, it will be my leaf level, whatever this level is. So the data comes in here 1, data comes in here 2, data comes in here 3. It is in order, it is okay, right? So then once the data has come in, we will now need to get into the situation where we have a problem. The problem comes when 4 tries to come. So 4 tries to come, it doesn't get any situation or space. So when that happens, what we will do is, there are 2 things we will do, and this was something that created a confusion yesterday. So let us be careful now. So what we will do is, this 1, 2, 3, 4, 1, 2, 3, 4, that was creating an overflow. We are going to split this in the middle and take these 2 elements to the left key or left node. That is, this is my left node. So 1, 2 will be going to the left node, and we will create a right node where we will keep this. We will create a right node where we will keep 3 and 4. Right? Unlike the last time where we had taken this and promoted it to the top, if you remember, or rather 2, we had taken 2 and promoted this to the top. Right? If you remember, we took the median, which was 2, and we took this 2 to the top. We are not doing that. We are saying that we cannot take anybody to the top. Everything is a data here. We'll have to keep the data here. Now we can of course do one thing, that from a this thing perspective, creation of the top perspective, what we will do is, the top is a router. Somebody has to route me to come to 1 or 2, 3 or 4. So who will route me? The thumb rule is take the rightmost element of the right split leaf. So sorry, take the first element of the right split leaf. The first element of the right split leaf is 3. So this 3 will go to the top, not as a data but as a router. Now when I say that, it is difficult for you to comprehend because 3 and 3 are the same. But imagine a situation where I had an employee number, employee name, then we had, let's say, salary. All of this is your data. All of this resides as 3 here. All of this resides here. Now what you are going to take up is going to be only this employee number. So this is only the employee number you will take up, so that the employee number will help us route where that employee number can be. So that's where I'm saying that the data is still kept there. What goes up is a router element, right, with which you can actually understand. So I hope you understand this part. So I have taken what? I have taken 3 as my router, and mind it, this 3 is not the same as this 3 in terms of being the data. It is more of a router. It's behaving more of as a router. And because I have kept 3 here at the bottom layer, I have kept 3 here also, right? So that means this layer is not divided. This layer has not promoted anybody above and removed it from here. I have not done that, unlike B tree, right? So I hope you understand now. So the rule for B plus tree is that when you split, you will split it here like this, and then the first element on the right subtree, that is what you will move up as the router element. So that's what moves up as a router element. Now the next element will come in, which is going to be 5, which will find a placeholder here. Then comes 6, and 6 will result in one more split. So 6 will come here, it will not find a placeholder. So what we will do, we will split the entire thing into half. So we will have one more half here where we will keep 5 and 6. Why? Because the overflow was because of 3, 4, 5, 6. So if we split like this, then 3, 4 will be in the left, 5, 6 will be in the right. So then this looks like this. Right child that we have created, the first element of the right child, that will move up as the router. So that will move up as the router means 5 will go here. That will move up as the router. Now if I see the connections, I forgot to make the connections. Let us make the connections. The connections are that from this pointer it will go like this, because 1 and 2 is less than 3. From this pointer it will go like this, because 3 and 4 is greater than equal to 3. So there is not more anymore greater than. 3 and 4 will be greater than equal to, because we are taking the same element, we will have to give it a benefit, right? So it will be greater than equal to. Next, 5 and 6 are greater than equal to 5, right? So we will use this pointer. So that is how your nodes will look, the pointers will look like. Next we take 7 lines of placeholder here. Then we have 8 will overflow, and that overflow will create what? If I keep bringing 8 here, it creates an overflow. So I will remove this and this. 5 and 6 will still stay to the left, and I will create one more placeholder for 7 and 8. Right, 7 and 8 will find a place here, and the first element of the right thing that we created will go to the top. Right, so that is what we will take from the right pointer now and put it here. Now 7 has gone, so then 8 comes. It has gone, so 9 comes. 9 will find a placeholder, and then we have 10. So when 10 comes, an interesting thing will happen. Seven, 8, 9, 10 will come here. So now an interesting thing will happen. What will happen is, we will split anyways the leaf node, we know what to do. we will not keep it here. We will create one more node, and we will have that node having 9 and 10. But at the same time, this 9 will have to go up, because this is the first node on the right child that we created. So 9 goes up here. So now we get an overflow here. Where? In the router layer. Earlier, what we were getting is overflow in the data layer. So in the router layer, when we get an overflow, then we will follow the same rule as B tree, not this rule at the leaf layer that we were doing. What was the rule? If you remember, we were taking this 3, 5, 7, 9. Then we were taking the median. Then we were taking the this element, the second element, and that we were promoting to the top. So we will do the same concept. So this will not be there. These two elements will not be there. So 5 will move to the top, and 7 and 9 will come here. 5 will move to the top. Remember, see, we are not keeping 5 there. We are not keeping 5 at the router layer. We are moving it to the top, because router layer follows the same rule as B tree, whereas data layer follows its own special rule. So 5 moves to the top. Now what we have to do is we have to rationalize all these links, because everything has changed. So all these links will have to be rationalized, and new links will have to be created. So this link will go here. This link will go here. 3 less than is okay. Greater than, this link is okay. 7, this link 5 and 6 is less than 7, so this is okay. Right? So 5 and 7 is less than 6 is okay. What else is there? So this link will go to here. 7 and 8 is greater than equal to 7. And then 9, this link will go here. 9 and 10 is greater than equal to 9. And that's your B plus tree. This is how you will construct your B plus tree. B tree, B plus tree, thumbs up or thumbs down? B tree, B plus tree. Is it okay? Understood now? কেউ তো কিছু লেখ। আচ্ছা, thumbs up. Good. Shayan is saying, will there be any quiz? Shayan, you have been first a lot of times. Don't worry about being first again. Anyway, you will be in the top 5 is what I know. So you'll anyway get the goodie bag. Okay. So now there are two things that we can do. I'll take your opinion. There are 56 of you here. There are two things we can do. One is I can do Tower of Hanoi. My whole point is Tower of Hanoi has come only once. If it is from a knowledge perspective that you still want to know about it, that is why the doubt came to me, because I see the doubt in Google Forms as Tower of Hanoi. So I will explain it. But if you think there are other topics I need to explain, I want to hear from this chat that should we go ahead and do Tower of Hanoi now? Or you want to give me some topics, because I don't have any more topics. There are some questions that are there which I will read out, and somebody has given after lunch some 2-3 things, so I will have to see that also. What should we do? Should we do Tower of Hanoi now? Yes or no? Let's do a yes, no. Tower of Hanoi, yes, no. Oishani Sen says yes. Tanmoy says yes. Ashmita, I said yes, no for Tower of Hanoi. Give me a yes, no for Tower of Hanoi. So, okay. If all of you are saying yes, we will proceed with Tower of Hanoi now. From exam perspective, I doubt. But from a knowledge perspective, you need to know. That's fine. Okay, where is this? Here. Heap short question is what Abhishek is asking. Suggestions for semester we will do after this doubt session is clear. Okay, so Tower of Hanoi is a classical problem, and I will tell you why it is a classical problem. By the way, all of you know by now that all my video lectures for everything is available on YouTube. Please visit there. Whatever we have discussed, everything is there also, right? We might have discussed it a bit differently or same way, I don't mind, but you can go there in case you want to know more about Tower of Hanoi, more about infix postfix. You can always go there. One module is left, which is graphs, which I will post it within. I am hoping that I will post it within the this year itself. Right. So only 1 or 2 lectures that will be there. We did graphs, we did hash, and then we have to do sorting. So those 3 things have to be done, which I will post it. So that is the module that is only left. Otherwise, module 3 tak you will have all the videos there. In case there is anybody new who does not know the videos, I'm sure you would have your friends who would know the channel name. Code to Win KB is the channel name. You can go there and actually subscribe or yourself, or even don't subscribe, just view the videos. That should be enough for you to probably do a refresher. Now let's start with Tower of Hanoi. In Tower of Hanoi, what we do is that this is something that is typically a game given to young children. How their cognitive skills actually grow. Can they be intelligent enough to use the minimum number of turns to do what? To do this. They need to do this. That is, take all the discs from one particular tower and move it to a target tower by utilizing one temporary tower. So the target tower is, let's say, B, by utilizing C. So that is what we will do. So we will say that this is Tower of Hanoi solution. I have taken from the left tower A and I have moved it to tower B by utilizing tower C. By the way, tower B is renamed wrongly as tower B, should be tower C. So I will take this and so that is what is Tower of Hanoi. Bottom line is, take this entire thing and put it here by utilizing tower C. So this is tower C. Right, so this is what Tower of Hanoi problem is, but it is not that easy, because you are not allowed to take these 3 discs in one complete go. You can you can only take 1 disc at a time. You can only take 1 disc at a time, and you can also not do like this. You can also not do this. That is, put this here and then take this and you will put this here. You cannot do this because you cannot do a larger disc on top of a smaller disc. So that is your restrictions. So with all these restrictions, your end goal is to produce, with all these restrictions, your end goal is to produce this, that this entire thing will go here. This is your end goal. How you'll do it, we will have to see that. So now what we will do is, we will need to understand that what is the complexity of the problem. The complexity of the problem lies in the fact that if we see how we are moving these disks, then the number of times that we will have to do the moves depends. The number of moves depends on what? Depends on n, that is the number of disks. More the number of disks, more the moves. So what is the formula? The formula says that I have to make 2 to the power n minus 1 moves when n is given to me. So if I have here how many? I have here n as 3. So 2 to the power 3 minus 1, which is 8 minus 1. I have to make 7 moves here to actually do what we just now discussed. So we have to take this entire thing, move it here in 7 moves. That is the most optimum number of moves. You can also do more than 7, which is fine, but that is the minimum number of moves that you will have to do to take this from this side to that side. So if 3 takes 7, n will take 2 to the power n minus 1. Then imagine for 64 as n, it will be 2 to the power 64 minus 1. That figure is this much. So I will have to make so many moves. This is not time, this is moves. And each move taking 1 second, it is 584.6 billion years it will take to solve a 64 disk tower of Hanoi. So that is why this is computationally so interesting to actually discuss about this problem. We can only discuss, we cannot implement this problem. We can only discuss about this problem just to make sure that we understand the gravity of the nature of recursion that is required to solve this problem. Earth is alive for around 4 billion years. So now you can imagine what is 584 billion years. Right? So that's the time it might take to actually solve a Tower of Hanoi for just 64 blocks. So now comes the solution. How do we solve it? Now, of course, all of you will say, इसमें क्या बड़ा deal है? We will take this C and we will use the intermediate tower, move it there. Then इसको लेंगे, इसको यहाँ पर रख देंगे. Then इसको लेंगे, इसको यहाँ पर रख देंगे. Done. हो गया. Yes, that is the answer. That is the answer. Right? So now, if that is the answer, then let us see that. Let us see from the beginning. What we are doing. So we are saying that A to C, one move will happen. A to C, that is, we'll take this and we will move it to C. C is my intermediate tower. Then we are saying A to B, one move will happen. So we will take this and move it B. Then we are saying that C to B, one more move will happen. So we will take C and move it to B. And that completes my Tower of Hanoi. So these moves comprise of what? Comprise of 3 moves. And 3 moves is what? 2 to the power, there were 2 disks, na? 2 to the power 2 minus 1, 4 minus 1. So these are the 3 moves with which we can solve a 2 disk power of Tower of Hanoi. I hope you understood how we solved it. Now come here, because now remember this, throughout this next whatever 10-15 minutes, please remember that a 2 disk problem can be solved in how much time? In 3 moves. A 2 disk problem can be solved in 3 moves. Just remember that. So come here. Here, when we give you 3 disks, then what happens? Then we will solve it by solving the smaller problems to solve the bigger problem. That is, we will say that there is a 2-disk problem I know how to solve. 3 moves. So I will solve the 2-disk problem, and whatever will be left will be 1 disk. That 1 disk we can easily solve after that. Right? So that is what we will do. We will solve this problem by taking advantage of the previous solution, which is the 2-disk problem. So that we will solve, and that should, once we solve that, then 1 disk will be left, that we can easily accommodate. So if you see that the 2-disk problem, if we want to solve, then we will take we are solving the 2-disk problem. The same set of steps we did in the previous slide we will do. What did we do in the previous slide? We said we will take A and move it to here. Or rather, A we will take here. 1 minute. Okay. Okay, so we will take A and we will move it to B. We will take A and move it to C. I am just following what is given here, and you can just follow this: A to B, A to C. And you can understand that's the same thing we did here, right? Here also we did the same thing. Right? To do go here, we utilize the intermediate. Here the intermediate we are trying to utilize. And what we will do is, we will take this there, and what will happen is A to B, A to C, then this will go to the right. So my intermediate in this situation I took was my tower B. So my positioning I did was to the tower C. Why? Because it's an intermediate step. Now 2 disks we are doing. We are not doing 3 disks. So the 2 disk final stage will be in an intermediate tower, which is here. So that's why I am saying that the 2 disk, when we took here from 2 disks, we did not utilize this as the intermediate and put it here. Unlike the last example, we utilized this as the intermediate and put it here, because we want to keep this as the final state. So we still have some moves left, so we'll have to utilize that, and that's why we are saying that we will keep this empty. Now this is gone, so these 3 moves is what we have already done. And A to B, we know now, it is easy. A to B is 1 move that we will have to make. This is the last record that is left, or last disk that is left. We are moving it. Now once we have moved it here, this is in the right place. Right? This is in the right place. So all we need to do is repeat our 2-disk solution. So this 2-disk solution that we had, right? We have to repeat it so that it now comes here. So what do we have? Intermediate tower. We have this as the intermediate tower, right? So this is our intermediate tower. So we will now do this 2-disk solution from here. We will now do this intermediate solution from here, and we will move it here. How? We will take the first disk. We will take the first disk. We will move it here. We will take the next disk. We will move it here. We will take this disk. We will move it back here. So all we did was we implemented that same 2-disk solution. Right? Again 3 moves. So total how many moves did you do? You did 3 moves here, 1 move here, and 3 moves here. That's what you did. So first time you took these 2 disks from the top, moved it to C. Then you moved A. From A you moved the larger disk to B, 1 move. Then the C you moved it back into B. So I hope you understand now that 2-disk problem can be easily solved if you have an intermediate tower with 3 moves. We have seen that, we have done that 2-3 times, we have done that now. Now before I move on, I just want to understand, is this part clear? If this part is not clear, you will not understand the algorithm. Yes or no? Okay, so now if that is clear, good. Now we will come to the recursive nature of this problem. So the recursive nature of this problem says that you are working with 3 disks. You actually employed 7 moves. With 3 disks, you did 7 moves. So if you have k disk, how many moves will you do? If you have k disk, how many moves will you do? So with 3 disks, if you do 7 moves, with k disk you will do 2 to the power k minus 1 moves. Right? So that is what the recursive nature of this problem tries to tell you. That now you know that 7 moves is translated to 2 to the power k minus 1. Therefore, you will have to think that from that perspective, you will have to think that with k disks given to you, you will make 2 to the power k minus 1 moves. And that is where the problem of recursion will start. So now let us see what is the recursive algorithm. The recursive algorithm says that tower of Hanoi will be actually implemented with A, B and C. So these are the 3 towers. So if we are going to move from A to B utilizing C as our 3rd tower. That is the problem. So our base condition will say that whenever 1 is left, right, that biggest disk is left, we will be moving that from A to B. That is our actual move. So whenever that is left, we will be moving that from A to B, if n equal to 1. Else what do? We do 3 things. Everywhere if you see, we have done 3 things. Right here if you see, we had done 3 things. First we moved the first 2 blocks. Then we moved 1 block. Then we moved back the last 2 blocks. So 3 things we have to do to actually solve the problem. So first thing is, we will move from A to C n-1 disks. So whatever number of disks are given, we take all the n-1. We keep only 1 disk away, 1 disk left. And all the n-1 we will take and move it to the last tower. That is what we did here. Right? So what we did here was, we took these 2 disks and we moved that into the last tower. We took these 2 disks we moved it to the last tower. That is, we took all the disks other than the last and we took that into the last tower. That's what we did, right? And this disk, if you remember, was here. Then we took this disk and moved it here. And then we took this entire set and moved it back here. Of course, not with that easiness. We have to do the 3 steps. I'm showing it to you in 1 step. This is what we did. So come back here. So you will do that first move with n-1 disks. You will do the movement of that A to B movement, that lone disk that was here, this disk, this will come here. Right? So that is this move A to B. And then whatever you brought here, right, will need to come back here. So that is your, from C, you are going to be using A. Again, the n-1 disks. That is your algorithm. Again, I will take a poll whether all of you understood this algorithm. Now I will draw the recursion tree for this. Once you say yes, I will draw the recursion tree. Tell me if you understood this algorithm. Answer, guys. I don't know whether you are hearing me. There is a huge delay, is it? Nobody is typing anything. Am I not audible? What happened? Okay, your responses are coming pretty late. I don't know whether it is a YouTube lag or it's multitasking. I'm not sure. But if you have understood the algorithm, then now I'm going to draw the recursive tree. So please be attentive. This is 5 minutes of work that will happen now with very high degree of attention, and Tower of Hanoi will be done. Okay, so let us start off. So I will now draw the recursive tree the same way I have taught you, in a timeline manner. So the recursion tree, when I try to draw, I will say Tower of Hanoi will be called with A with A, B and C with n-1, or with, let's say, Tower of Hanoi will be called with A, B, C. Instead of n-1, I will take 3 because we started with 3 disks. So that is my Tower of Hanoi. Now, why did this happen? This happened because somebody called from main the Tower of Hanoi. So that resulted in this. Now, if you remember, I had said that in this particular example, what will happen is we will have to do ABC3. I mean, every function of Tower of Hanoi call will have to do 3 things. One, they will have to do this ACB n-1. They will have to do this, and then they will have to do this. So these are the 3 things that they will have to do. Now, if I am here and I have to do this, so I have passed it that I want to do Tower of Hanoi of ABC. So I have to do Tower of Hanoi of ABC means that this function gets called. If this function gets called, then this function should be doing these 3 things. Right? So this function will be doing these 3 things. So what are those 3 things? The 3 things are So what are those 3 things? When this function gets called, it has to do 3 things. Those 3 things are Tower of Hanoi will call Tower of Hanoi with A, C, B and n-1, which means 2. Why ACB? If you see the algorithm, it is ACB. In fact, I will write the algorithm here in the next page so that we can look it up rather than coming back and going here. So I will write it here. So the first step is Tower of Hanoi ACB n-1. The second step is move A to B. And the third step is Tower of Hanoi CBA n-1. Tower of Hanoi CBA n-1. So we will be taking these algorithm from here and we will try to do this. Okay, so now we have taken the first one, which is this. So this is the first one we have done, ACB and then 2. Now this ACB and 2, immediately when I call this, what happens is internally that function gets called, means that function's life starts. So this function's life starts means the function is supposed to do some work. That work it is trying to do now. What work is it trying to do? It is trying to do, the function will do the same work, this set of work only. Every function will do this set of work only. So it is trying to do what? TOH ACB. Right? So what is A? A is A. What is C? C is actually B, na? So I will write B. And this will be C. I hope this part you understand. Be careful on this part. Right? So the sequence of this is ABC, right? But ABC has not come. ACB has come. So actually your C is now B. So I have written ABC because I was supposed to do A. I was supposed to do C. I was supposed to do ACB. So I was supposed to do ACB. That is actually ABC, na? So I have written ABC. And then I will say that I will reduce this disk by 1, n minus 1. So this is my first task of this particular person completed. Now what will this person do? This person will do the second task. What is the second task? The second task is move A to B. But here B is C. So move A to C. Right? So I'm sorry. My bad. I missed on one part. Because we call Tower of Hanoi ABC1, that will initiate a lifeline for this function again. Right? And this function will do its work. What is the work? Work is Tower of Hanoi, and we will remove this because the work has not got over. This also the work has not got over. Right? So we will say that Tower of Hanoi will be called again with ACB n minus 1. Now what is ACB? ACB is really ACB because it has come as ABC. So ACB n minus 1 means 0. Now when that happens, ACB n minus 1 0, it actually means that this function will exit. This function will exit with what? That boundary condition, the base condition. When it is 0, actually it will not become 0. It is at 1 that we are doing the exit. So at 1 it will exit, which means if you see here the base condition is at 1, move A to B. So at 1 move A to B means that when this function was called, I need not have called this function. When this function was called, this function will exit by doing what? Will exit by doing move A to B. Right? So this function will do a move A to B. So this function will do a move A to B. Why? Because you have given it 1. So what will happen? Your move A to B will move this particular disk. This particular disk will move to B. This is what will happen. Right? So next you will actually come here, and this completes this particular function's lifeline. Right? So this completes this particular function's lifeline, means that I have no work to do after this point for this particular function. So this particular function has got over. Now if this particular function has got over, then the first job of this particular person is over. So everybody will do 3 things. So this job is over. Now this function's second job will start. So the second job of this is to do a move. Right? So the second job of this is to do a move. So it will do the move. Because if you remember, our algorithm says second job is to do the move. So move will happen from A to B. But here B is C. So move will happen from A to C. Right? So that is my second job. So when I do this, when I come here, move will happen from A to C. So it will move this here. So this is also done. So this is my second job. So if this is the second job, then my third job is Tower of Hanoi CBA. So I will do a Tower of Hanoi CBA. So Tower of Hanoi CBA would mean that I have to write it like this. tower of Hanoi CBA. C was B, so CBA, and then I will put 1 here. So this is what I will call, this immediately starts a lifeline, and this creates what? A move. Move what? A to B, which is B to C. Why? Because it is 1. 1 means base condition. So this function will get over. So this function will get over. That means that the third job of this function is also over. Third job of this function is also over. Right? So this move B to C is what we will have to do now. So let us do that move B to C. So we will do this move B to C. Next, so what are we done with? We are done with this function. So this function's timeline will now end. This function's timeline will now end because 1, 2, 3, that job of this function is done. Right? So this is now done. Now this function, that first job is complete. So it will now start its second job. The second job is to move A to B. So it will move A to B. So when it moves A to B, we will do that move. So this will be moved from A to B. That's all. Next, the third work will now start. The third work of this function will start. The third work says tower of Hanoi CBA 2. That is the third work. As soon as this starts, its timeline starts. So its timeline will say that tower of Hanoi, then we will have to do ACB n minus 1. So ACB n minus 1 is ACB n minus 1. Right? So that is what we will do. ACB n minus 1. This will start a function, and this will basically make the move from C to A. C to A, because we are doing a to B, C to A. So that means this job is done. This job is done. So this function's first job is done. So let's do that C to A movement. So we will do a C to A movement. Right, so we did the C to A movement. Now what we will do? Now the second job should start. So the second job is this. So this tower of Hanoi CBA2, its second job is to move A to B, which is C to B. Right? So C to B we will have to move. So let us go here. We will move C to B. Done. Come back here. So the second job of this function is also done. Now we will come down. The third job of this function is to do tower of Hanoi CBA n minus 1. Now CBA n minus 1 is A, B, C, 1. Right? CBA n minus 1 is ABC1. ABC1 would mean this lifeline will start, which will do a move because we have 1 here. Base condition is satisfied. A to B movement will happen, and that is going to complete this third task also. So this third task will be also completed. So we will do a move A to B. So our job is done in terms of moving the 3 disks. So we have done the 7 moves, but we will have to unwind the stack completely. So move A to B, our third task is done. So if you see here, this function is over, which completes 1 2 3 here, 1 2 3. So this function is also over, and because this function is over, therefore this function is also completing its 1. This is the 1, this is the 2, and this is the 3. Right, so this function is also over. So that is the stack unwinding that will happen, and your Tower of Hanoi is solved. Right, so that is how it works. Tell me, you understood it or didn't understand it? All gone off to sleep, is it? Oishani says yes. Except for Oishani, everybody is sleeping. So you didn't understand, is it? That's why you are keeping quiet. If you don't say, okay, I understood, how will I understand? That's the problem with this chat, na? Help me understand that you have understood or didn't understand, whatever it is. This was specifically asked, and I asked you that whether you want to do it. You said yes. Now is it clear? Good, fantastic. So now let me take up some problems that have come, and then you can tell me what you want to do. Otherwise we'll just break off for 15 minutes here. What we have, I have received as other responses is, somebody is asking, AVL anyway I completed, linked list we have done, column major, what is the address of 3/2th element of a 3-4 matrix given that the base address is 2000? Provides its integer value. I think this was given by Shayon. So this is the problem. I will try to put this problem here. So I had put some placeholder. I don't know whether I have some placeholders. Let me use this placeholder for this problem. Okay, so the problem looks like this. So difficult to manage this. Okay, so now it is visible. What is the address of the 3/2th element of a 3/4 matrix? So Shayon, I think you have given this problem. M is 3, N is 4, because we have 3 cross 4 matrix. You are being asked with I and j as 3 and 2. And we are asking column measure. So let me quickly check the formula of column measure. I remember it was n-1 star j. Can somebody give me the formula? I'm not finding the formula. Should have been here. Anybody has given the formula? M star j plus 1. Yes. M star j plus 1 for a column measure with I think 0 index. Yes. So M star j plus 1 is M star j plus 1. That is going to be 3 into 2 plus 1, which is going to be 7. 7 multiplied by did it say anything? Nothing is said about being an integer, so I'll assume it is an integer. So 7 multiplied by 4, 28. So 2028 is coming as the answer, which is not a part of the option. Now if I take one index calculation, then M star j minus 1 plus 1. M star j minus 1 plus 1. Oh, I made a mistake, I think. Not plus 1. It is plus I. Yes, M star j plus I. Why 1? Why did I take 1? Yeah, it is M star j plus I. So I is 3. So 3 2s are 6. 6 plus 3, 9. 9 4s are 36. It will still not match. So this will become 36. Otherwise it will be like this: M star j minus 1 plus I. M star j minus 1 plus I will be the one index formula. So that means it will be 3 star 3 plus I, which is 3, that is 9 plus 3, which is 12, into 4, which is 4 2s are 8, 48. So 2048, that is also not a part of the answer. So unfortunately, Shayan, it is not matching with any of the answers. I know that is the reason you have given it. If it would have matched, you would have not given it. So you have to assume that this is wrong. There is no other way. We have checked with I0, we have checked with I1. I mean, we have checked with 0 index, we have checked with 1 index. There cannot be any other way. There is nothing tricky about this question, I see. M by n is given, Ij is given, column measure is told, 2000 is told, unless they are on a 2-byte system. If they are on a 2-byte integer system, then you will get this answer. I told you, right? We don't know what integer they are. I took 4. If I take 2 as a 2-byte system, then I'll get 2012 as the answer. Actually not. I will not get 2012 also. 9 to 18. I'll get 2018. So 2018 will be the answer. On a 2-byte system, 2018 will be the answer. That's it, Shaun. That's all the best I can do. Yeah, so if you can take a 2-byte system, since Shaun it was not mentioned, we have to assume something. From the options, we'll have to assume a 2-byte system. Okay, so Shaun, okay, we'll move on. Next question that has come in. Tower of Hanoi is done. Construction of B plus tree I have done. Farhan has written something. If we implement binary search tree by array, binary search by array and binary search tree. So he's saying that I'm going to do binary search using array or binary search tree. Then the array is okay to do, or BST is okay to do. Where do we do the binary search? Because both of them have the same complexity. First of all, that's the basic galtis, Farhan. Both of them don't have the same complexity. In a binary search tree, your worst case complexity, in an array, you understand that for binary search, you are dividing and conquering. That's why it will be log of n. That we have already established. This is for array. And for binary search tree, your worst case complexity is this, a skewed binary search tree, which is order of n, not log n. Your assumption was we are doing both as order of log n. No, binary search tree worst case complexity is order of n, which is larger than log n. Therefore, utilize array for doing binary search, then binary search tree. That is the answer, Farhan. If in case you are here, please respond okay or not okay. That is the answer. Okay, so now I get to see a lot of postfix, prefix, construction things that are there. Other than that, I don't see any other problem statement. So you guys now tell me what all you want to do. Postfix, prefix, infix. Give me what do you want to do? Everything is done, everything is okay. Then we will just break off from live and join a different call where I will talk about suggestions, where I'll talk about next steps, etc., etc. Anything else to discuss? Anything else to discuss? Please type it on the chat window. Otherwise, we will now join another call where we will talk about other things. Okay, so I think most of you are saying okay then. So what I'm doing is I'm going to post this link. Now don't run away. Please come. All of you please come here. Let me make some important announcements. We will log off from this live. We will log off from this live and we will come there and we will discuss certain other things. Because I want to hear you also, which is why I want to move out of this chat mode. Not heard you for so many days. So I'm posting a link here. Okay, you should see it in your WhatsApp now. Please join here. Don't run away. Please join. I'm closing this live stream now.